Welcome, ladies and gentlemen, to our lecture on mechanical waves. Mechanical waves are waves that travel through some medium. Okay? When a mechanical wave is moving through a medium, the particles of the medium oscillate, but they don't move along with the wave. Okay? A wave is a structure that allows energy to move through a medium without also moving mass through the medium. So we have three types of mechanical wave. The first is a wave where the particles move perpendicular to the motion of the wave. So you can imagine if I had a string here, and I took one end and I shook it up and down like this. In fact, let's make it even simpler. I just shake it up and return it to its starting position. What I create is a wave in the string that looks like this and travels down the string. Okay? In this case, each piece of the string just moves up and then back down. Okay? And this piece is up right now, and then it's going to move back down. And in the future, this piece is going to move up and then back down. Okay? And this wave, this kind of structure here, moves along like this at some velocity, but each piece of the string only moves up and down. Okay? So the particles of the medium, the string is the medium, move perpendicular to the motion of the wave. This is called a transverse wave. Okay. The second kind of wave involves particles oscillating in a direction parallel to the movement of the wave. So in this case, imagine, say I have a column of air, and I take and I push it like this and then return back. Okay, so I have like a plunger and I have a column of air. Then what I do is I move the air over, and the air moves and it gets denser. And then all the particles here push them back, right? So the air moves this way and then it moves back. And then the particles further down the line, they move this way and then they move back. And then they move this way and they move back, all along down the line. And this structure, this little pressure piece, moves like this with some velocity, but each little piece of air is just oscillating like this, moving back and forth. Okay? This is called a longitudinal wave. Okay? And the most common example of this one is sound. Sound is vibration that makes particles move in this oscillatory fashion of a longitudinal wave and create these little pockets of pressure. Okay, so you'll also probably hear me call sound a pressure wave, and that's because what it does is it creates these periods of oscillating pressure. Okay, but we'll get more into that later. For now, just know transverse wave means that the particles of the medium move perpendicular to the velocity of the wave. Longitudinal wave means that the particles move, they still only oscillate, okay? They still don't move along with the wave. They still just oscillate. But their oscillations are in the same direction as the velocity of the wave, okay? Or not in the same direction as the velocity, because the velocity is a fixed direction, right? In this case, it's moving to the right. So the oscillations are in the same dimension, or the same unit vector as the velocity of the wave. Okay, so if this is x hat, this velocity of the wave, the oscillations are taking place in x hat. Okay, so they're moving in positive and negative x hat direction. Okay, and if in the case of the transverse wave, if this is x hat and then this up and down is y hat, the particles move only in y hat. Okay, and then the last kind of wave, imagine if we had like a tank of water and I had a big board here. I had water like this. And then I push the board like this and back. Then I create this wave in the water, just like an ocean wave, right? That does this. And this. Okay? And what these particles do is they move in both the transverse and longitudinal directions. And what ends up happening with these is that the particles move in a circular motion. Okay? So these particles move circular. And so then what happens is my wave, this shape here that I've created, it still travels along with a velocity this way, but the particles move in kind of little circles. Okay, this one, the example obviously that we want to use in Hawaii is an ocean wave. Okay, the waves in the ocean are this type where they're kind of a combination of two, and I don't really have a name for this one. This is just the kind that's not one of the other two, right? So anytime you have both kinds of motion, you're going to have something, more complicated that involves both longitudinal and transverse motion. Okay, and indeed, the waves that are in the ocean are mechanically much more complicated than something like a sound wave. Okay? So when I gave examples of the kinds of waves, I was showing kind of a single pulse, right? I take the rope and I move it up and down once, or I take the column of air and I just kind of punch the little plunger once, or I have the column of water and I just move that board or whatever one time. Okay? But imagine that instead of just doing it once, I have, say, the string, but now it's attached to something on one end, and I shake that other end with some set frequency, right? So in this case, let's say I'm shaking it up and down with some set frequency. Well then, instead of just the one pulse going through this string, what I'm sending is multiple waves all back to back through the string, right? And we've seen this in people's workout videos and things like that, right? People will take ropes and shake them like this, and you can watch the little waves go down the ropes, right? They look like this picture here. They're not just straight, and they don't have just one pulse down. You have many, many waves going through, okay? We call these periodic waves. Just like our periodic motion was the same motion repeated over and over again, a periodic wave is just repeating that same wave over and over again. And what I get is waves with some given frequency, okay? So we have some number of waves per second, all right? And all along this string, each little piece of the string is still just moving up and down, right? So all these little pieces here in the trough, they're all just moving up and down. But each one of these waves is going along with this velocity, right? So you can picture this structure right here moving along with this velocity v, okay? Now the speed of the wave moving down a string is always going to be lambda f, okay? Where lambda is the wavelength. The wavelength is going to go from the same spot to the same spot. So it's the distance that covers one period, okay? So in this case, I'm marking lambda from crest to crest here, okay? But you could also have, let me get some of these arrows out of here. You could also mark lambda, say, from trough to trough like this. That's also lambda. You could also mark it from, let me extend my wave out a little bit. You could also mark it from some arbitrary point, halfway up here to halfway up here, right? Or carrying this out even further, halfway up the downslope here to halfway up the downslope. As long as it's in the same position. You notice I'm halfway up the upslope on this one, right here. And on this one, I'm halfway up the downslope. So my lambda isn't from here to here. It's from here to here, okay? So always the same point in the motion. Just like for our period with our simple harmonic oscillator, it was always the time to get back to the same point in the motion, right? The same place with the same velocity. So you're in the same spot in the cycle. With the wave, it's the same thing. The wavelength is from any given spot in the cycle, the distance to get to that same spot in the cycle, okay? And then the frequency would be how many of the same spot in the cycle cross some given point in a matter of time, okay? So if I have this spot and these waves are all moving along like this, how many times do I get a crest that passes through this spot in a second would be the frequency. So we could also have a periodic longitudinal wave. And it creates, instead of the shaking string like this, these areas of more and less density. Okay? Like this. And indeed, this is what sound is, okay? So you have something over here that's vibrating back and forth with some frequency F, and it creates these pressure waves that have wavelength lambda and then some frequency going past some given point or getting to some given point. And the frequency is going to be this frequency, okay? And the same thing with the string here driven. The frequency is going to be the frequency that's driven back here, okay? So as a wave travels, each particle that it's using to move along experiences the same kind of periodic motion, but at any one point in time, the particles are all in different phases of that periodic motion, okay? So if you look at my string here that has the wave going through it, at this moment in time that I've drawn, this one is at the maximum amplitude, A, right? But this one is at some other phase, okay? It's not A, it's some other X, and it's going down. And this point right here is at some other phase. It's some X, and it's going up, right? And so all these different particles are all at different phases in the motion, okay? Now, there are spots that are in the same phase, right? This one is at A, and this one is at A. But for any given spot, it could be at any point in the phase of the cyclical motion, okay? But each little spot is going through simple harmonic motion, okay? It's just going up to A. Well, I picked a trough. It's either going down from equilibrium by A or up from equilibrium by A, okay? And so we have the equilibrium here in the middle where the string was before I started shaking it. And this is simple harmonic motion. So each piece in the wave is experiencing simple harmonic motion, but the wave itself is kind of the conglomeration, the effect of all of these pieces pushing on each other and moving this wave along through the medium. Okay? So if I have a wave that's moving to the right, like this one I've drawn up here, then at any given time, for any given spot, the spot that will be in the same phase that the spot to the left was at time t is t minus x over v. Okay? So the time when any given spot will be at a crest, or be at some specific point in the phase, is going to be t minus x over v, okay? To make it equal to the time that a spot on the left was in that same phase, okay? So then our equation for the wave is going to be y of x and t, okay? It's a function of both position and time. It's equal to a cosine omega, and then the t piece is t minus x over v, okay? For a wave moving to the right. And this is what we call the wave function, okay? It describes the wave at all points where the wave exists and for any time, okay? It gives the time evolution of it as well. So we can pick any point along here and describe it at any point in time as well. Now this makes a lot of sense for the transverse wave because it oscillates in the perpendicular direction to the wave velocity. But in the case of the longitudinal wave, where the oscillations are occurring in the same direction as the wave, it might not be so intuitive, okay? Here, let's draw it this way. So my little particle oscillates from equilibrium, okay? In this case, we can still use this same equation, but now y is this, okay? So we just tip y so that it goes in the same direction as v, but it's still just an oscillation from equilibrium, okay? And this equation will still describe that longitudinal wave just as well as it described our transverse wave. And the x-coordinate in the case of the longitudinal wave is going to be the coordinate of the equilibrium position, okay? So then the coordinate of any given particle in the longitudinal wave will be whatever x is that we decided on plus y, okay? plus this oscillation away from x. And this equation here will describe those oscillations. Okay? So now let's play around with this equation a little bit. The first thing we can take note of is that cosine of minus theta is equal to cosine of theta. Okay? This is just a property of the cosine function. So then we can flip the difference inside if we want to do that. So let's write this as omega x over v minus omega t. Okay? And then this x over v term can be written as, remember, omega equals 2 pi f, right? And remember that v equals lambda f, okay? Then we could write this as 2 pi f x over lambda f, okay? And then remember that our wave number, k, is equal to 2 pi over lambda, right? And so then this piece is equal to kx, okay? And so let's replace that up here. It's kx minus omega t. So now we have a pretty nice simple function to describe our wave motion, okay? And now, if our wave was moving to the left instead of to the right, the only difference would be that v would have been negative instead of positive. And so moving right with x hat this way. So moving left, moving the other way, the v would have been negative, and we would have gotten a cosine kx plus omega t. And so we have this equation to describe the motion of the particles as our wave goes by. This is what we call our wave function. Okay? And it's important to note here that the particle speed and the wave speed are different. The wave speed depends on the properties of the medium and the wave. And ultimately, remember, the wave speed is v equals lambda f. Okay? Now, for the speed of the particle, we would take the derivative of whichever one of these equations is appropriate. Okay? And that would give us the speed of the particle. But then let's play with these a little more. I'm gonna get rid of the one moving left. Okay, let's just play with the one for the one moving right, because they're not ultimately very different. So let's use this one, and let's do the second derivative of this equation with respect to time. Okay, so that equals d dt. And then the first derivative is going to be minus omega a. Oh, minus goes away. Sine kx minus omega t. Okay? And then that's going to be omega squared a sine minus omega squared a sine kx minus omega t. Okay? Oh, I wrote sine. This is cosine, right? We go back and forth as we take derivatives. And then the minus came out from pulling the minus omega in here, okay, from the chain rule. And then if we take the second derivative of this with respect to x, we'd have d dx. And then the same kind of thing is going on here, right? In the first derivative, I'm going to get the minus sign from going derivative of cosine. I'm going to get a minus, this time k a sine kx minus omega t. And then when I take the next derivative from sine back to cosine, I'm going to get another x out. I'm going to get a minus k squared a cosine kx minus omega t. Okay? And then if I take a ratio of these two things, I'd have d squared y dt squared over d squared y dx squared is equal to this stuff on the right? And the a's and the cosines cancel, and what I get is omega squared over k squared. And then remember that k is equal to 2 pi over lambda, and omega is equal to 2 pi f, which is equal to 2 pi v over lambda. Okay? And these 2 pi's over lambdas canceled, and then what we end up with here is v squared. So then I can do some real simple algebra here and get d squared y over dx squared equals 1 over v squared d squared y dt squared. Okay? This is what we call the wave equation. Okay? And this equation is true for all waves. And the v in this equation is always the translational speed of the wave. Okay? How fast the wave is going. This equation is an incredibly important equation in physics, and anytime it occurs, we know that we have a wave traveling along the x direction at some speed v. Now, the speed of a mechanical wave is going to depend on the properties of the system. So in general, the speed of our mechanical wave is going to be v equals, and then it's the restoring force that's restoring the particles to equilibrium divided by the inertia that resists the restoring force, and that's going to be in a root. Okay? So for a wave on a string, the velocity ends up being the force of tension divided by mu, where mu is the mass per unit length of the string. Okay? For a longitudinal wave in like air or something, or water or a fluid like that, v is going to equal the bulk modulus divided by rho, which is the density of the fluid. And the bulk modulus describes a fluid's resistance to being compressed. Okay? And then for a solid, this bulk modulus piece is replaced by kind of a different analogous property for solids. And these properties of the medium are going to always define the velocity of a wave for a mechanical wave that's moving through a medium. Okay? So we said before that energy is being transferred by waves while the particles just oscillate, right? But how much energy is transferred by the wave? In a periodic wave, we have waves constantly moving through the medium with some given frequency, right? So I have some, wow, those are really not uniform. Imagine they're uniform waves, okay? Moving with some frequency through the medium. So the amount of energy transferred by these waves will depend on how long we continue to send the periodic wave, right? How many of these waves get to say this point will dictate how much energy has been transferred through this point, okay? So instead, we can look at the power, the rate of energy transfer, right? Power is energy per second. The power is always changing because the wave comes from simple harmonic motion of its particles, right? So the force that's going up and down on this particle is always changing, right? Simple harmonic motion is differing forces, differing accelerations all the time. But we can take an average of this kind of ever-changing power delivery, and we get this equation for the average power transfer of a transverse wave. And that's going to be P equals 1/2, and then root tension times mu, okay? So if this is on a string, and this mu, again, is the density per unit length of the string, omega squared, a squared. And that's going to be our power transfer along a string, okay? For a longitudinal wave, we're often more interested in the intensity of the wave, okay? And a longitudinal wave moves outward from some source. So if this is the source of the longitudinal wave, over some angle, theta, if it's directed, and if it's not directed, it moves out radially like this, okay? Waves that go out like this, pressure waves. And the intensity is the average power per unit area, okay? So this intensity is equal to P over 4 pi r squared, where r is the distance out from the source here, okay? Or to some point here, r. Okay? That's going to define the intensity. And the power in this case, it's not this one. This was for a string, right? The force of tension and the mass per unit length, they don't make any sense for a longitudinal wave, right? So this isn't for that. This power is generally going to be the power that the waves are driven with by the source, okay? So if the force is driving waves of some frequency at a power of 200 watts, then the power out here is going to be the 200 watts in here divided by 4 pi r squared, okay? So now let's move on to wave interference. Let's consider what happens when we have multiple waves in the same place. So waves obey a principle called superposition. And superposition says that the effect of multiple waves on the same spot at the same time is the effect that we get by just adding up the waves, okay? So if we have, say, a wave coming from here, and it goes out like this, and a wave coming from here, and it goes out like this, to get the effect of these two waves on this spot right here, I just add up the two waves. So my function, y total, my wave function for the two waves together is just y1 plus y2. Okay? Now, things don't always work like that, right? Sometimes when we go to add different things, our y total might look like y1 squared plus y2 squared in a root, right? Or it could look like y1 times y2 in a root, right? That could be y total. There are lots of ways that things could work, but for something like waves, they obey superposition, and superposition says that they work like this. You just add them up. And of course, our wave equation wasn't a vector equation, right? So we don't have to even do vector addition. We just add the wave functions. And there are many things in physics that obey the principle of superposition, and it always works the same. The effect of multiple interactions together can be found by just adding each of the different effects together. So we saw before that forces obey the principle of superposition, right? When we wanted to get the net effect on an object that had multiple forces acting on it, what did we do? Well, we used Newton's second law, and we just added up the forces, right? And the net effect of multiple forces was just the sum of all those forces, okay? That's superposition. So then if I have two waves and they both have this sinusoidal wave function, right? Remember our wave function was y of x and t equals a cosine kx minus omega t, right? Then they can be in different phases at different spots, right? So any given spot that I pick, the two waves might be in different phases. So imagine that I have two waves going through the same spot. And let's say they're both sine waves, like this guy, okay? And they can be at different phases on that spot. But let's say for a given spot, one wave going through looks like this, okay? Where this is time, and this is y. And then the other wave going through the same spot looks, as best I can draw it here, just like it, okay? So the peaks match up, and the troughs match up. Now if I add these together, so that's y1 going through, and that's y2, then y total, superposition says, is just y1 plus y2. Well, in this case, if I add them together, I end up with something, a wave. I'm really trying to draw these so they match up here. I have a wave that has now twice the amplitude, okay? Because here, if say, let's say the amplitude of this one is plus 5 at the crest, and the amplitude of this one is plus 5 at the crest, then this amplitude, by adding them together, is going to be plus 10, right? And the same thing's happening here in the trough, where the amplitude is negative. I get twice the negative, okay? This is called constructive interference, right? I add these two. They're in phase, okay? They're in the same part of the cycle, and I get a bigger peak, okay? That's called constructive interference. Now, I can get constructive interference when they're not in exactly the same phase, if they're in close to the same phase, okay? But then you can see the other situation I could have is I have the first wave like this, okay? And then what if the second wave is coming through like this? So this is y1 and this is y2. Well, now if this one is plus 5 here, and this one is minus 5 here, then the sum, well, that's something even I can draw. There's just nothing happening, okay? They canceled each other out perfectly. Now, if they had different amplitudes, if I had a plus 5 here and say a minus 2 here, then what I'd end up with is some smaller wave, right? One that's maybe this is minus 3, okay? But in either case, when I add them together, because they're perfectly out of phase, they're exact opposite phases, they're causing each other to go away, okay? That's called destructive interference. So I still just add the waves, just like I did before. Superposition says I just add them together. But now the phase that they're in means that when I add them together, the result is a wave with a smaller amplitude, okay? Or in the case that they have the same amplitude, the same frequency, and they're just 180 degrees out of phase, okay? This, from trough to crest, this is 180 degrees. If they're just exactly 180 degrees, or pi radians, out of phase, with the same frequency and with the same amplitude, what I end up with is no wave at all, okay? So now let's take a little aside and look at what happens when a wave gets to a particular boundary, okay? So let's consider my string again, where I take the string and I just move it up and back like this, so I send a pulse through the string like this. Now, the pulse moves along and it gets to some point here, and let's say this point is fixed, all right? The string can't move up and down here. It's attached to the wall at a fixed point here. When this pulse gets here, it's going to hit this point, and it's essentially going to reflect off of this point. And what I'm going to end up with is, as it comes back, I'm going to have a pulse that's opposite, okay? So it hits this fixed point, and I get this opposite thing coming back when this thing went in. If, on the other hand, I have the same situation, and it gets to the end here, but now this thing can move up and down, okay? Then when this pulse goes in, it's going to cause this point to move up and down, just like I did when I started the thing, right? So then what happens is what comes back out, because the end moved up and down, is a wave that looks just like the first one, going back the other way, okay? And these different constraints on particular points in a wave system are called boundary conditions, okay? And the behavior of our waves will always depend on the boundary conditions. So now, think about in these two drawings. Let's say I sent the one pulse in and it got to this fixed point here, and then it reflected back opposite. And I sent another wave at some time after the first, so now at some point in the middle they're going to meet. And as they're moving along, I have one wave that looks like this, the second wave that I sent down the string, and then coming back, I have the reflection of the first wave, right? Well, superposition says I just add the waves right here, okay? And so what happens is I have one wave, so at one point in time, I have the waves like this, and this one's going this way, and this one's going this way. As they meet each other in the middle, what I get is a flat string, okay? Superposition says add them up. One has a positive amplitude, one has a negative amplitude, so what I end up with is nothing when they meet. And then after they pass each other, I'll have the one on the bottom still coming back this way, and I'll have the one on the top still going this way, okay? Now, in the case of the string that was free to move on one end, where I got the identical wave reflected, okay? Then, when these two things meet in the middle, I'll get a bump that's twice as high, okay? And then afterward, after they meet, I'll of course have my two smaller bumps, the one going this way and the one going this way, okay? And again, this is just superposition. All I have to do to figure out what multiple waves in the same place are going to do is just add up all the wave functions, okay? So now imagine that instead of just sending two pulses, I have a driving force at one end of the string that shakes the string with some given frequency, sending waves of the same frequency down the string. And then I have a fixed end at the other end, okay? So my string goes to this fixed point like this. Okay? And over here on the other end, I have something shaking it like this, constantly around its equilibrium point. Okay? Then these periodic waves travel down this string and they reflect back from the fixed point at the end, and we'll have constructive interference at some points, and we'll have destructive interference at some points all along the string. Okay? And what happens is this thing comes in, and it reflects the opposite wave. And we get waves traveling along in both directions. Okay? And what it usually ends up looking like is I have these spots that don't move, and then I have these spots that are oscillating up and down. Okay? And you can do this and see it for yourself. And your book has some really nice time-lapse photos of this as well. So you usually end up with what looks like kind of a blurry moving string here, and you have these points that are fixed. These points are called nodes. And nodes happen to be in places where the string doesn't move at all, because the interference always is destructive interference that adds up. Remember, the waves are moving like this and like this, right? And it just so happens that at these nodes, the interference is always destructive to the point that there is no wave at these points, okay? So when the one, if this is the equilibrium point, when the wave moving this way looks like this, right? It's going up to its thing. The wave moving this way looks like this, so that these distances are the same, and our node right here still doesn't move, okay? And so what we end up with is something that looks like this picture down here, where we have kind of loops, and then we have spots, nodes, that don't move. And then we have, in between the nodes, these spots with maximum movement called antinodes. Okay? And then you can see these other spots, they have movement, but always less than an antinode, right? They're vibrating up and down, but they don't get all the way to the maximum amplitude where there's maximal constructive interference. Okay? And we call this a standing wave. Okay? In a standing wave, the nodes are always half a wavelength away from each other. So this is always lambda over 2. Okay? And the antinodes are also always lambda over 2 away from each other. Okay? And the node, say this node here, and the nearest antinodes, this distance is always lambda over 4. Okay? Let me erase just to make totally clear. The distance between the node and a nearest antinode is lambda over 4. Okay? 1/4 of a wavelength. And our wave function for a standing wave of this type ends up being y equals a for the standing wave. Okay, it has a different amplitude than the amplitude that was being driven right here because we have constructive interference at places like the antinode. Okay? Sine kx sine omega t. Okay? Now, for some points, this sine x is 0, and then the y is 0 at all times, right? Those are the nodes. But for other values, for every value where this sine x isn't 0, or this sine kx isn't 0, then y has some value that's going to vary with time based on this other sine function. Okay? And so you can see there are only certain points where sine kx equals 1, and so y varies between a and minus a. Okay, those are the antinodes. And then for any other point, this sine kx is something between minus 1 and 1, okay, or between 0. It has a magnitude between 0 and 1. And that's all these points between the node and the antinode, okay? And then this sine function is going to make them vary from whatever their little a is. So you can think of this as defining the a for a position, okay, the amplitude of that position. And then this piece, this sine omega t, is going to describe the variation between whatever the a for that position is, okay? So if I draw from a node to a node here so that I can draw it bigger, and I have this amplitude, so we have our equilibrium position here. At the antinode, this is going to be a above and minus a below. And then at this point here, we have some, we'll call it a prime, oops, not minus, a prime above and minus a prime below. And it's something that's less than this a of the standing wave, right? And then this other sine function tells me that what's happening is this little piece of rope is vibrating up and down at this amplitude that's defined by this first piece, okay? And so what I get is these fixed points and then these things of varying amplitude just vibrating up and down like this, okay? These pieces in the middle. So now, let's modify this again and think of a string that's fixed at both ends, okay? And let's say this string has a length L. I'm going to want to draw on this, so let's not do that. Let's just say the string has a length L. Okay? So a lot of things that vibrate are fixed at both ends. And strings that are fixed at both ends are, of course, found on things like pianos and guitars, and in Hawaii, of course, ukuleles, right? So if we pluck a string that's fixed on both ends, it has certain frequencies that it will vibrate at. And this comes from our boundary conditions, the fact that it's fixed on both ends. This fact that it's fixed on both ends means that a standing wave on it must have wavelengths that cause a node at either end of the string. Okay? So a standing wave is going to create nodes on a string, right? But by fixing both ends, what I'm saying is that I must have a node that spot and that spot, right? Because it doesn't move. By definition, it must be a node. And so that means that a node will be at intervals of half a wavelength. So we have to break L into pieces that are half wavelengths, okay? So that means that L equals n lambda over 2, okay? Where n equals 1, 2, 3, etc., okay? Integers. So if n was half a wavelength, I would just have this, right? The thing would be vibrating up and down like this, right? Because neighboring nodes are half a wavelength apart. If L is a full wavelength, then I could have a node in the middle and vibrations like this, right? If L was 3/2 of a wavelength, then I could put 2 nodes into the middle like this and have these 3 sections that vibrate like this, okay? Up and down. And you can see that as I make n bigger, I'm making the wavelength shorter and shorter. But always L has to be broken into some number of half wavelengths to get a standing wave on the string, okay? So the possible standing waves on this string of length L all have wavelengths of lambda equals 2L over n, where n equals 1, 2, 3, etc. Okay? So there are infinitely many possible waves, but we have to just keep making the wavelength smaller and smaller in order to keep getting more and more possible standing waves on the string. Now the lowest frequency is going to come from the longest wavelength on the string. And remember, that was when the length of the string is a half a wavelength, when the whole thing was vibrating as one. So I'll draw a little mini picture up here. That was when we had this situation, right? Where we have the vibrations like this with a node at either end. If that's the case, then we're going to call this F1, okay? And then the frequency is going to be V over 2L, okay? Remember, V equals lambda F, right? And the lowest frequency comes from the longest wavelength, which is n equals 1, so then lambda equals 2L, right? And then V would equal 2LF, so F is equal to V over 2L, okay? And so that's for n equals 1. That's for our longest wavelength that we can have a standing wave on the string for, okay? This is called the fundamental frequency of the string. So F1 here is the fundamental frequency of the string. And then all other frequencies that the string can have, okay, that can maintain a standing wave on the string, will be Fn equals n F1, okay? There'll be some integer multiple of the fundamental frequency. And again, this n equals 1, 2, 3, etc. So when we pluck a string, we generally aren't applying a normal mode, though, right? So if you imagine I have the string, I'm going to draw the mini picture up here again. When I pluck it, I don't pull it right in the middle and make this like perfect sinusoidal curve here, right, to make the first fundamental frequency. I pluck it somewhere over here and it looks more like this, right? And then I let it go and it vibrates. And so what happens is that at t equals 0, I need to sum up a certain number of my possible standing wave frequencies to get a wave that looks like this, okay? And I can always do that for any kind of wave like this. I can always add up other waves of varying frequency to get that wave. Okay, I can add it through some number of sine functions, and that's called a Fourier transform. Okay, and so that tells me I can add up a whole bunch of sine functions, and I can eventually get this. And the sine functions that I'm going to add up are the wave functions for all of these different frequencies that I can have a standing wave at on this string. Okay, and so I'm going to add up a whole bunch of these different frequencies to get this weird curve that I have to start with. And it's going to be some number of these. Remember, there's infinitely many of these, so I can just keep adding higher and higher frequencies until I get something that looks just like this curve at t equals 0. Okay? So I add all of those wave functions together, and then when the string vibrates, it vibrates with all of those standing waves incorporated into the vibration of the string. Okay? So all of these normal modes vibrate on the string. Oh, I think I didn't tell you guys that was a normal mode, huh? These lambdas that create standing waves on the string, these are called normal modes. Okay, it's just a name for this thing. And the string has, of course, we said infinitely many normal modes, but they are very specific values, right? It's not all values. It's only certain values that create this standing wave on the string or normal modes. So when I pluck the string in this strange way, I add up normal modes until I can get through superposition this funky curve that I've made by pulling up on the string. And then when I let it go, it vibrates with all of those normal modes, right? All of those normal modes evolve through time, just like they would if I just was able to put one of them on the string, okay? But then I get on the string a superposition of all of those different normal modes for the whole time that it's vibrating, okay? In a musical instrument, this creates what are called overtones. And this is the reason that the same note, which has a set frequency, okay? That a musical note is a particular frequency of sound. But a given note sounds a little different on different instruments, right? You could hear a string plucked on a guitar and know that it wasn't a string plucked on an ukulele. And that's because there's different sets of overtones also vibrating on the strings, okay? So different instruments have different tonal qualities that affect their sound. So we're going to stop right there for today. And in the next lecture, we're going to expand on these ideas of periodic waves and standing waves to talk specifically about sound.